Hello everyone. Here is the video for test review 1 for organic chemistry 2. Let's start with question 1. We would like to identify the molecular formula for a hydrocarbon with mass of 132. So we already know that we have only hydrogen and carbon. So we can just follow the rule of 13 for calculation of molecular formula. So 132 divided by 13. The answer here is the quotient is 10, then 130. The remainder is 2. So we should have 10CH and 2 extra hydrogen. So the formula is C10H12. Always we should double check the formula with degree of unsaturation to make sure everything is right with our formula. Degree of unsaturation for this compound is equals to number of carbon plus 1 minus number of hydrogen by 2. 11 minus 6 is equals to 5. So it is an acceptable degree of unsaturation. If we have negative or fractional, then something is wrong with our formula. So here is the answer for question 1. Let's take a look to the question 2. We would like to find the molecular formula for this compound that we have mass spectra for that. The parent peak is 170 and we also have m plus 2, 172. And if we take a look to the pattern, we see they are identical. Because they're identical, it means we have bromine in our compound. And always for bromine and chlorine, we do calculation based on the first parent peak and first isotope, which for bromine is 79. So because our molecule has one bromine, I'm going to subtract mass of bromine from mass of molecule to find out what is the remaining is 91. Then we can do rule of 13 for 91. 91 dividing by 13. The answer is 7. And the remainder is 0. So we have 7 carbon and 7 hydrogen because the quotient is 7. So the formula is C7H7. We also had one bromine that we subtracted from the original mass of molecule. So C7H7Br. And if we calculate degree of unsaturation for this compound is equals to 4. So here we should write formula number of carbon plus 1 minus number of hydrogen plus halogen 1 bromine, we don't have nitrogen, over 2. 8 minus 4 is equals to 4. Here for question number 3, we have 5 compounds and we would like to match them with the IR. To answering this question, we need to take a look to the functional group. For example, compound A has alkyne and we have a terminal alkyne. So we should have a CH for C triple bond, which is around 3300. And we had to take a look to the spectra. This is the peak for terminal alkyne at 3300. And just to make sure we don't have these peaks for the other compound, we can check them and we don't see anything around 3300. So the first spectra is belong to compound A. We can also see two compounds, they have OH, B and D. But compound D also has a carbonyl group. We can see OH here and we can also see OH here. If the OH overlapping with this CH, normally it belongs to the carboxylic acid. But in addition of that, we should see the peak of carbonyl group, that we can see it here. So this spectra has OH and carbonyl. The other spectra doesn't have carbonyl, it's just OH. So the one is just OH is compound B, and the one is OH and carbonyl is compound D. So this is D, and this is B. So right now we have A, B, and D. Let's find out C and E. Both of them, they have carbonyl, but C also has cyanide. Cyanide C triple bond N and also C triple bond C. They normally appear around 2200. Which we can clearly see it here. This is cyanide, so it belongs to compound C, and the other one, it should be compound E. Aldehyde group, you see the carbonyl here at 1700. Also, aldehyde functional group should show a CH of aldehyde around 2800. So this is how we can match the compound with IR spectra. For question number 4, we would like to find out the relation between hydrogen. Are they unrelated? Are they homotopic, enantiotopic, or diastereotopic? Take a look to these two hydrogen. This CH2 is attached to two identical group. When CH2 attached to two identical group, they are homotopic. If CH2 attached to different group, then they are enantiotopic. And if CH2 attached to two different group, but at least one of them, it has chiral center, like here, then we have diastereotopic hydrogens. And if you take a look to the last one, HA and HB here, they are completely different. One is next to the bromine, another one is just attached to a carbon. And these two, they are completely unrelated. Here is how we can simply find the answer for this type of question. For next question, for question 5, how many NMR signal we should see for H NMR and for carbon NMR for each of these compounds. For compound 1, this CH3, they attach to the CH and they're identical. So I call them A. Then this CH, B. Then this CH2, C. And then this CH3, D. So we see 4 different signal for H NMR. All of these 4 type of CH, they show also signal for carbon NMR. In addition of that, we have unprotonated carbon, the carbonyl group here. So we should see 5 signal for carbon NMR. For second one, it's a little different. This is one type of hydrogen, methyl. This methyl also is one type of hydrogen. So let's call them A, B, this hydrogen, C, but we have chiral center. When we have chiral center, hydrogen for CH2, they are diastereotopic. They are different. They show two different signal. Then one of them is D, another one is E. So instead of 4, we actually see 5 signal in H NMR. But if we take a look to the type of carbon, then we don't need to take a look to the chirality because CH2, it has only one carbon. So we don't need to be worried about this chirality in this example. So we have one type of carbon, 2, 3, 4, and 5. So we have 5 H NMR signal and 5 carbon NMR signal. In question 6, I would like to find the splitting pattern or multiplicity of hydrogens. We start with A. A is CH3 and the next atom doesn't have hydrogen. So it has 0 neighbor, 0 plus 1. It is 1, so it is a singlet. B. Hydrogen attached to B, it has one neighbor, C. So 1 plus 1 is 2. So we see a doublet for B. Same thing for C. C has one neighbor, it is B. So 1 plus 1 is a doublet. D is CH2 and E is CH3. D has 3 neighbor, 3 plus 1 is a quartet. And CH3 has 2 neighbor, the CH2 for D. 2 plus 1, 3, it's a triplet. So this is the pattern in this compound. In question number 7, we have compound and we would like to match them with HNMR. Compound A is different because we have benzene ring and we know benzene ring it show between 7 to 8 ppm. So we can easily find the compound A. This is compound A because we see peaks for aromatic ring in this NMR. For the rest of this, we need to take a look to the number of signal and their pattern and match them with NMR. For example, compound B, it has 1, 2, 3 signal. And all these 3 signal, they don't have any neighbor. The neighbor doesn't have any hydrogen. So here, this is CH3. This one is CH2. And this one again is CH3. So these 3 signal, they don't have any splitting pattern. They're singlet. So we need to find the NMR here. It doesn't have any splitting and it show only 3 signal. So this one cannot be. And this is the answer. So for compound B, this is our spectra. But we need to double check the rest of compound. Here we have doublet. Here we have doublet. A number of signal doesn't match as well. For compound C and D, they have very similar pattern. These two CH3, they are identical. So we see one peak. This CH, another peak, and CH3, another peak. So we should see three signals. Same thing for D. But their difference is in C, methyl attached to the oxygen. In D, isopropyl attached to the oxygen. So the chemical shift of CH and CH3 will be different for these two compounds. We know the isopropyl group, it shows a doublet and a septet. Doublet with 6 hydrogen because CH3 and CH3 they have one neighbor. 1 plus 1 is 2. So this 6 hydrogen for 2-methyl, we see a doublet with 6 hydrogen. And this hydrogen, it has 6 neighbor, 6 plus 1, septet. So we should take a look to the NMR here and we see doublet with 6 hydrogen, septet with 1 hydrogen. And again, we see the same pattern here. But which one is belong to C? Which one is belong to D? The key for answering this question is the chemical shift for attachment to the oxygen. Attachment to the oxygen causes the signal appear around 3.5 to 4.5. Here CH attached to the oxygen. So the septet with 1 hydrogen, it should be around 4. But in C, we should see the CH3, a singlet, appear around 4 ppm. So let's see which one is singlet around 4. This compound, the singlet is appear between 3.5 to 4. So this is belong to compound C, this signal. And in next spectra, here we see the septet is appear around 5. So this is belong to compound D. So the CH attached to the oxygen and instead we see the methyl is not on that range anymore. And for sure the remaining one is compound E, and we can also find out E easily because E, it has 3-methyl here, they're identical. So we should see a singlet with 9 hydrogen. And we see a singlet with 9 hydrogen. This is how we can match the NMR with the available structure. But let's see the next question. Question 8. We have the formula, we have the H1 NMR, and we need to find out the structure. The first step always is calculation of degree of unsaturation. Number of carbon plus 1. Here we don't have halogen, so just 12. Number of hydrogen by 2. So we have 10 minus 6, it's 4. And we can easily see that we have benzene ring in our structure. Benzene ring, it has one ring 3 pi bond, so the degree of unsaturation is matched with benzene ring. The pattern is one doublet with 2 hydrogen, another doublet with 2 hydrogen. This pattern is belong to benzene ring that has substituent on 1 and 4. Then each of these hydrogen, they have one neighbor and they show doublets. And the molecule is symmetry, so the left and right hydrogen, they are identical. So each peak has 2 hydrogen and it is doublet. Then let's see what is the groups we should attach to this benzene ring. We see a singlet with 3 hydrogens, so we just have a CH3. We also have a CH3 is triplet. When it's triplet, it means the neighbor has 2 hydrogen. And we also see a CH2, which is quartet, so the neighbor is CH3. So of course these two ethyl groups, they are the same thing. So we have one ethyl group and one methyl group. In addition of these pieces, we have one oxygen in our formula. Should we attach oxygen to the methyl or to the ethyl? It is very clear that ethyl attached to the oxygen because the peak is around 4 ppm. So we have CH2O and we have CH3. So on one of these two positions, I put CH3. On another position, we should have OCH2, CH3. This is the structure for compound X here in this question. For question number 9, we want to rank this compound based on their stability. So compound A is a diene, compound C is a triene, compound D is a triene, and compound B is also diene, but it's also cumulated. And we know cumulated alkenes, they are very unstable. So B should be the very last one in this rank. And of course, after that, we should have A because it's diene. And between C and D, we need to make decision which one is more stable. C and D, both of them, they have 3 conjugated bond, but we know from the alkenes that when we have alkene with more substituents, our alkene is more stable. So because both of them, they have same type of conjugation system, then the one it has more substituents will be more stable. D and C. And the last question in this test review is question 10. We need to predict the reactant or product in this following reaction. For reaction A, we use a strong base, so we can have elimination reaction. On both sides of this bromine, we have hydrogen. So we may have elimination from here or we may have from here. So we have 2 possible products. This one and this one. And of course, when we have these 2 possibilities, conjugated compound is a lot more stable and conjugated compound form as a major product. Normally the unconjugated product, it doesn't form in this type of reaction. So the answer is cyclohexadiene. For reaction B, we have addition of bromine to the diene. We need to find out the kinetic product and thermodynamic product. Kinetic is 1 and 2 addition, so we just simply take one double bond and we add bromine to that double bond. So we have Br here and we have Br here. And we know addition of bromine is Nt, so we may want to show it in Nt or trans positions. And thermodynamic is 1 and 4. So we should put one bromine on carbon 1 and one bromine on carbon 4. So between carbon 2 and 3, we should put double bond. Then we have one bromine on carbon 1 and one bromine on carbon 4. For reaction C, we have a Diels-Alder reaction. One pi bond here, one pi bond here, and one pi bond here. They move simultaneously. So this one comes here, this one goes here, and this one goes here. So we have an alkene here, and we have 2 methyl on that double bond. On the right side, the triple bond converts to the double bond. We also have 2 CO, CH3. This is the answer for this question. For reaction D, again we have Diels-Alder reaction. Carbon 1, 2, 3, 4, 5, 6. So we have a cyclohexene. Carbon 2 and 3, they're double bond. And 5 and 6, we have cyanide. They should be cis, and because they would like to go to the endo position to interact with these pi bonds and the pi bond of diene in the transition state, they should be in the back of molecule. And then chlorine, it should be front. If we want to know why, we need to compare it to the cyclic diene. If we have a cyclic diene, this CH2 is always going to the bridge and it is up. Right now, instead of CH2 in this molecule, we have one hydrogen and one chlorine. So this chlorine and hydrogen, they're going up, and this hydrogen and the other hydrogen, they're going back of the molecule. So the chlorine should be in the front, and the cyanide, they should be in the back. And the last reaction, we have the Diels-Alder product, and we want to know what is the reactant. So we see this part in the molecule here. And always the part it has double bond is belong to the diene. But because it's bicyclo, it means we had a cyclic diene. So this is carbon 1, 2, 3, 4 for diene. And 1 and 4, they attach to each other by oxygen. So it's a cyclic. And on carbon 2 and 3, we also have bromine. So this is the diene for this reaction. Thank you for watching this video.